In this tutorial, I will be explaining the neural networks, how they work, the calculations we must do for the complete and good behavior of the neural network. So, what is the structure of the neural networks? Firstly, in the feed-forward neural networks, we'll have layers. We'll have here the hidden layer, here the input layer, and the output layer. Okay, this will have the positions 0, 1, and 2. Also, in each layer there will be some neurons. For example, here we'll have a neuron in the position of the layer 0, another neuron, and another neuron. But the neurons, they have two parameters. The first, as I said, is the layer, and the second is the position in the layer. So here, for example, we'll have the position in the layer 0 and 0. Okay, so this will be 0, this will be 1, and this will be 2. Then the activation, the neurons, can be subdivided in the net neuron and in the out neuron. The net neuron, okay, of a neuron will be the most simple value. But if we want to activate this neuron with the activation function that I will be explaining later, we will get the out of the neuron. Okay, this is an important notation that we will be using with the calculations. Then also we have the biases. These are very important for learning because if we want to solve a regression problem, the end will be for the bias. The bias will have help for getting the end of the rect. Okay. The bias will be also as the neurons, the same notation, the layer and the position. And finally, we'll have the weights that they are in charge of connecting one layer to the next layer. All the neurons from one layer will be connected to all the neurons to the next layer. For example, here we have a wave, and the wave will have a notation of the layer and the first position and the second. So, for example, if we want to assign this wave, we'll know that this is in the position 1 of the layer and position 0 in the layer. So if we want to get the wave, this wave, it will be in the position of layer 0. Okay, this will be layer 1 of wave, and it will be in the position 0 of the layer, and it will connect the position 0 and the 0. And this, for example, will be this, because it connects the position 1 of the second layer. And it will help us also for the learning, because they will be in charge of the M. Okay. So now I will explain how a neural network will be working. Firstly, we'll have some input data that will be assigned in the input layer. It could be stimulus or the data we want to analyze for resolving or predicting something, for example, digit recognition. Okay, then we'll have the hidden layers and the output prediction. This will be the output prediction of our neural network, that each neuron will have a value stored. And then we'll be updating the network, okay, with some inputs, the weights and the biases that are not currently visible will be able to do the feed-forward update. So we'll from the input layer in this direction will be updating. Okay. Then we'll calculate the error, because as I said, we can have supervised learning, that this is what we will be using for now, and we'll know the response when training. So we'll calculate the error, the mean squared error, and we'll learn. This is the most important part, the backpropagation, that will update the weights and the biases for learning in this direction, okay? From the outputs to the inputs, the opposite direction of the feed forward. So now we'll start with the math, with the calculations, that is the complex thing. Firstly, we'll use this example of neural network, but there are more complex neural networks. When we do a problem, for example, of recognition, the neural network is very, very big. So firstly, we'll need to initialize the weights and also the biases, okay? We'll do it in an interval of -1 and 1. Okay, so each weight will have a value. As I said, this is the layer 0, 1, and 2. Okay. Then we'll need to assign the data or the stimulus we want to analyze in the neural network and predict an output in the input layer here. Okay, we'll put the values, and then we'll execute the feed forward. Okay, as you see here the formula. Okay, as you remembered, we want to achieve this. You can see here. Okay, here this is A and L, this is the L, and the M is the weight. Okay, so how do we do this? For example, if we want to get the value, because now when we assign the inputs in the input layer, we know, because of the fact that we initialize the weights and the biases, we know the weights and the biases. Okay, but also with this we know the input layer, so we know in the position 0 all the values of the neurons. Okay, so what we'll do, if we want, for example, this value that is in the layer 1 and in position 0, this is okay. So if we want to get this value, we'll need to do the sum of the multiplication of this weight value with this. So as you can see here, if we want this, it will be equal to the sigmoid that I will explain later of this. Okay, wait, plus the next neuron multiplied by this weight that is in the position 0, the same, and this, and this. Okay, and we'll need to add also this bias that is in position 0. Okay, and we'll have the value. Okay, so we'll need to do this through all the neurons, because when we have this neuron and this neuron with the formula, we'll be able to also have this and this, because we have these neurons. So it will be in this direction. Okay, and what is the activation function? The activation function could be a lot. I have chosen sigmoid for this tutorial. this is the sigmoid, and the graph is something like this. Okay, from values that are very far from x equals to 0, there will no where there won't be any important difference. But from values that are very similar to 0, it will have very important variations. So also there are also activation functions like the value, but I will be using this. And so with the value that we have calculated before, we will do the sigmoid. Okay. And now we'll need to do the error of the output layer. With the feed forward, we'll be able to have some values here. So we'll know, as I said, with the supervised learning, the response. For example, this. So we'll need to do the error, that in this case, it will be the difference, that is 0.1 squared, plus the difference here, that is minus 0.1 squared. Okay, and we'll do this multiply by this. Okay, and k, that is the number of outputs, that is 2. And now we'll need to do the backpropagation. Okay, we'll need to decrease this error that we calculated, and this is the main important part, because is where our neural network will be learning. So we'll have, as I said before, two notations, this and this. If we apply for the feed-forward value without the activation function, we'll have the net value. But if we apply the activation function, we will have the out value. The out value is the most important, and it will be used for when we update the network. But for the derivatives that we will be doing later, it's useful to have the net value also. So if we want to backpropagate the error, okay, and we want to decrease, we'll execute the gradient descent, okay, of the error. And how do we do this? We'll need to do the partial derivative of each weight, okay, of the error with respect to each weight. If we do this in a more simple formula, we'll have this formula, okay, that you see here. And it's a complex formula, but now we are going to put it in a simple way. Firstly, we have this derivative, the error with respect of the out of the neuron. And if you see here, as you remember, this was the formula of the error. So if we do the derivative, we'll put this here, and it will be this, okay, and this is the derivative of the error, and you can see here that is this. Also we have the derivative of the out with respect of the net value, and if you see here, if we want this derivative, it is the derivative of the activation function, and if we are using the sigmoid, the derivative is this. You can't trust me or do the calculation, but is this the derivative. And finally we'll need to do this derivative, that is the final value, that is this. We need to define some variables that are very important for the backpropagations, that are the delta output of layer. This is the error signal of a neuron, okay, of the weight. This delta don't depend on the previous neuron, is the same as this, but without the dependencies of the previous neuron. Okay, so we'll have here a value. Okay, these deltas, and we can calculate them with this formula. But as I said, this derivative we can do it when the weights are in the output layer. So these weights we can update with this formula. But these weights, because of the fact that they depend from the previous weights and the rest of the structure of the neural network, we can't use this formula. So this is the reason why we are simplifying this with the delta, because as I said, this is the delta. So we can put this as this. That is a simple formula, and this formula we can use it also for the hidden layers, because we can get the delta from the hidden layers with this formula. Okay, we need to sum this value multiplied by this, and also this value multiplied by this, and we need then to apply the sigmoid derivation function of this neuron. Okay, and with this we'll get the value of this delta. Okay, and with this delta, now with this general formula of the delta multiplied by the neuron, we can easily update all the entire weights of the neural network. If we want to see the overall formula, is this hidden layers, but you see a complex formula, but it's simple because this is this. So only, as I said before, the formula is the delta, but in a hidden layer, multiplied by the neuron. Okay, and with this we can change all the weights, but now we'll need to do the biases. We need to do the error the derivative of the error with respect of each bias that we have. If we do this in a simple formula, we'll have this. Okay, the error with respect to the net, and the net with respect to the bias. So we'll have this derivative that is only the error signal of the neuron. And as I said, we can calculate the error signal with these formulas, and we'll finally do all the backpropagation system, because we'll do how much the error, the bias must vary depending on the decrease of the error. So we want to decrease the error. And finally, with this gradient descent that we have done, we'll update each weight and each bias with this value that we calculated previously. And we also need to multiply this derivative by some learning rates that, for example, they need to be very low. Okay, because if we are training a lot, we don't want to decrease all the error for one training. We want to decrease a little bit because there are other trainings sets that we want to also learn. So how will be training? We'll have some parameters. Okay, we'll have the dataset, also the epochs that are the loops through all the training data. Okay, and then we'll have the learning rates that I said before, and this I will be explaining in the next tutorial. So firstly, we'll need to iterate through all the epochs, okay? Through the epochs, and in each epoch through all the datasets. Okay, and in each dataset we need to do some things. First of all, we need to get from the dataset, we need to get the data we want to put in the input layer. So we need to get the data and assign the inputs with the data of the dataset that we are currently looping. Then when we assign this, we need to do the feed forward, okay? And with the feed forward, we'll get the outputs of the neural network. Then we'll need to calculate the error with the outputs, okay? And also we'll need the desired outputs, okay? Because we know what is the response we want from the neural network. So from the dataset, we'll get also the desired outputs. And with the error, here we'll be assigning to a float, okay? We'll need to back propagate the error. And finally, update the weights with the variation we calculate with the backpropagation. And with this, we need to do it through all the datasets, and we finally decrease the error, and the neural network will learn. But also, we'll do it. We can make it faster and more efficient with the gradient descent type, because we are currently using each update of the weights, each dataset from each dataset. So we are using the stochastic gradient descent. But these two are better, and we'll see it in the next videos. And also we can use optimization algorithms. Okay, I will put an example now, okay, for how can we use neural networks. For example, we want to do decay recognition, okay. We have here a 2. So with these 2, we'll make an array with all the pixels, okay, and the color of them. So if, for example, the 2 is made in white, it will give from 0 to 1 how white is the pixel. So 0 will be black and 1 will be white, and this will be assigned to the inputs, okay, this array. Then we'll do the feed forward and get the outputs, okay. And if our neural network is currently trained, these outputs will be correct, and it will have a good prediction of the neural network. But if our neural network is not already trained and it has only initialized the values of the weights and biases randomly, we need to train it. And how do we train it? We'll need to do the backpropagation, and we'll need to train, okay, this number. So For number recognition, we'll have here the pixels inputs, and the outputs will be 0, 1, 2, 3, 4, 5. Okay, and here it will give us the prediction. For example, when we do the feed forward, if the neural network is already trained, it will give, for example, if we have the 2, as I said, 0.1, 0, here it will be 0.95, for example, 0, 0, 0.1, 0.2, 0.1, 0. So we'll get this value because the neural network predicted that this is the most high prediction. Okay, and with this I think we have finished. Now you know how to create a multilayer neural network, and in the next tutorials we'll learn how to improve this training.